Hi, this video is to help you complete activity 10.1 in your science book, and it's to help you understand how light energy may be converted into other types of energy. So at the beginning of the year, we worked with a device called a radiometer, which looks like the object in the picture shown in front of you. And the idea of the radiometer is it's a partial vacuum bulb that has a wire post, and then there are four paddles that are connected together, and they're allowed to spin on that post fairly quickly and easily. The paddles, if you notice and remember, have a dark side, so black side, and a white side to them. And we did an experiment with these in class to see how we could get it to move, and did it make a difference as to what happened when we shine the light on different parts of it. So I want you to think about this, and as we go through these questions, if you need to pause to think about the answers, then feel free to pause before we move on. So the first question is, what happens when light shines on the radiometer? Well, when we did our experiment, we decided, depending on how you shine the light on it, nothing will happen or the paddles will move. So if you shine the light onto the black side of the paddles, the light energy that's focused onto the black side of the paddles of the radiometer will cause the blades to move, and so then they gain kinetic energy. So the light energy, we will abbreviate as LE, helps to generate kinetic energy for the blades when it's shined onto the onto the black side of the paddles. So the second question then is, once it's spinning, would it spin without the light shining on it? Again, this was part of our experiment to determine what would happen if we took the light away and then we timed it, and then what would happen if we shined the light onto the white side when we were trying to get it to slow down. And if you remember at the beginning of the year, for almost every class, I believe, when we took the light away, it actually would quit spinning faster than if we shined the light on the white side. And our hypothesis there was that some of the light from the white side was reflecting onto the back side, thus causing it to continue to spin. But eventually, if we took the light away completely, the blades would spin for a little while, and then eventually they would stop spinning, so they would lose kinetic energy. We will be exploring this more in our second book as to how this actually works when we talk about Newton's laws of motion. This thing has been argued and contested for many years as to how and why it works. All right, so the big question we're trying to focus on is, where did the radiometer's kinetic energy come from? Because we know that all the energy we have is all the energy we have. Law of conservation of energy says that energy can neither be created nor destroyed, but it can be converted or transferred from place to place, or from system to system. So that means this energy to get the radiometer to move has to come from somewhere. So think about, where did it come from? I'm hoping that you were thinking that the light energy was the cause of this thing moving. So what happened was, the focused light shining on the dark side of the radiometer blade provided the kinetic energy, as the light energy was absorbed and then converted to kinetic energy eventually. So we're going to begin again to discuss this process more in our next book. So we're going to leave it as far as that goes right there. So the next question we have is, how can light be connected with the radiometer's kinetic energy? Because it seems weird that you just shine a flashlight on this thing and it starts to move if you shine it focused light on the dark side of the paddle. Well, what happens is the light energy is actually indeed being converted and helping to cause the radiometer to spin. So that's how they're connected together. And here's another little dilemma and something for you to think about. Someday when you purchase a vehicle, I know some people really like to have a dark colored interior in their car. Some people like to have a light colored interior in their car, depending upon how hot you like it and what time of the year it is, in Wisconsin at least. So if we had two identical cars, one was white and one was black. So we're talking black outside, black inside, okay? Or white outside, white inside. And they're both left in the sun on the same day, parked next to each other. Which one's going to get hotter? Explain your answer. Well, quick little story. My Aunt Marita, who used to live in Las Vegas, at one time, she purchased a really nice black on black Mercedes Benz. And she couldn't figure out why it was such a good deal. Remember, I said she lived in Las Vegas. In fact, the selling price was $5,000 below book value. And the person only had the car for about a month. So she didn't understand what the problem was because it was still under warranty. It ran and drove perfectly. Well, she figured out shortly thereafter that the next day, because she purchased it late in the evening, the next day, after she went to get into it after work, she discovered very quickly as to what the problem was with driving a black car with a black interior in Las Vegas in the summertime. So the answer to this question is the black car would definitely get much, much hotter than the white car. The black car would get hotter because the dark colors are going to absorb the light energy, which then can convert into thermal energy. The lighter colored vehicle with the lighter colored interior will reflect the light energy. And then the reflected light energy doesn't have a chance to heat up the interior of the vehicle as much as the absorbed light energy does. So the absorbed light energy converts into thermal energy, increasing the temperature of the car. And that's what my aunt found out very quickly was that car was horrible. She drove it for about a month, and then she too turned around and sold it for a little bit of a loss from what she paid for it because she just couldn't handle the heat. No matter what she did, the air conditioning couldn't keep up. So when cars get hot, what type of energy is increased? So if a car's interior gets hot, what type of energy is increased when we're talking about this scenario? Well, hopefully you figured out that it was the thermal energy. Not a trick question, just a question. All right. So now if we go back to the cars again, which car has more thermal energy? The black car or the white car on a sunny day? I'm hoping this is an easy one. You're like, well, we get it. We know the hotter car has the more thermal energy. You're right. The black car definitely has more thermal energy than the white car on a sunny day. Now at nighttime, after the cars have cooled down for several hours, they're probably the same temperature again. They have a difference as the day warms up and the temperature goes up because of the sunlight. And so the next question is, why is it that the black car has more thermal energy? Well, the reason why is because the darker colors are able to absorb the light energy, and then that light energy can be transformed or converted into thermal energy, which then gets released from the surface into the interior of the car, which then gets into the person and heats them up. So the black car has more thermal energy because it's absorbed more light energy, and the light energy is transformed or converted into thermal energy in the car as released from the dark surfaces of the black car. So these are your notes for the day that I'd like you to put into your book. And it's kind of important that you know these notes. And I put these in Google Classroom for you. So light energy can be thought of as both a type of energy and a mechanism for transferring energy from one place to another, like sound energy and thermal energy. When light is absorbed, its energy is transferred to the object absorbing it, where it appears as a different type of energy, and therefore light can make things start or keep going. Light energy can be transformed into Ke, kinetic energy, Ce, chemical energy, or Te when it is absorbed. So if you think about kinetic energy, think about the air molecules moving faster and faster. As those air molecules are going faster and faster, they are gaining thermal energy. And chemical energy, if you think about that one, think about plants and how they use the sunlight in the process of photosynthesis. Okay? All right, now, for activity 10.1, here's the main event. What you're supposed to do is fill in this chart, and you're supposed to identify the type of energy transformations for each scenario. So the first one, you have a plant growing. Think about photosynthesis, what we just talked about. The second one, we have a digital camera. It's important that we say digital camera, not film camera, but I'll show you both answers. The third one, we have a person suntanning. And the fourth one, we have a solar cooker. So please take a moment to pause the video and fill in the chart. All right, so let's talk about these answers. I kept this really simple, So for me, for the plant, I said the light energy converts into chemical energy, which the plant then uses for photosynthesis. So you can see the rest of the explanation in blue. The camera, on the other hand, if it is an old style film camera or a glass plate type camera, the light energy converts into chemical energy to produce the photo, which you then need to develop. For a digital camera or a camera like on your cell phone, the light energy converts into electrical energy, and then that takes it and produces the photo for you. And again, you can read the rest of it in blue on your own. For the suntan, light energy converts into chemical energy, which then causes your skin to change colors. And finally, for the slow cooker, if it's cooking something, probably involves heat, so your light energy converts into thermal energy. And slow cookers can be valuable tools when camping or if you just like to go outside and cook your food without burning a lot of fuel. They don't cook as fast, but they do cook well, if you get a good one. All right, so the next thing we have one more question. The conclusion, can light be considered a type of energy? Explain your answer. So I'm going to pause for a moment and give you a chance to think about it. All right, I'm hoping that you figured out that yes, light is a type of energy because it can be transformed to and from other energy types such as chemical energy. Think about like fireworks. Kinetic energy, okay, it can convert into kinetic energy, cause things to move. And think about thermal energy. Alrighty, so we have finished activity 10.1, and I hope you have everything answered in your book. Thank you.